Hello, good morning, everyone. I'm Fabiola Greve, professor of the Federal University of Bahia. Thank you very much for coming to this presentation of Rachid Guerraoui. It's a great pleasure to receive Rachid Guerraoui in Brazil, talking with our SBRC community. Rachid, thank you very much for coming. It's a great honor to have you here among us. So I will introduce you to the audience. The first thing that you should know about Rachid is that he is a very good runner and a very good surfer. The second thing is that Rachid is simply the most brilliant distributed computing scientist of nowadays. So let me tell you a little bit about him. Rachid is professor, indeed, in computer science at OPFL, l'École Polytechnique Fédérale de Lausanne, where he leads the distributed computing lab. So Rachid has written some very interesting books, like Reliable and Secure Distributed Programming that I use in my lectures. Rachid has formed and keep forming great computer scientists. He worked in the past with great labs, such as Le Centre d'énergie atomique at Saclay in France, and HP Labs in Palo Alto, MIT, and has been elected ACM Fellow. And Rachid is also a professor of Collège de France, l'école prestigieuse in France. And I've seen a number of interesting lessons that I recommend you. I think that they are through YouTube. Rachid has also awarded a Senior European Research Council grant and a Google Focused Award. I think that's why he's succeeded to have so good guys and good girls working with him. And that's why also I think Rachid has a number of best papers on great conferences in distributed algorithms. So Rachid, be welcome to Brazil and SBRC. Let's start your video presentation, and afterwards we are going to debate with the audience. Thank you very much.
Hello, I'm going to talk about Bitcoin, and the goal here is to demystify the Bitcoin protocol from the distributed computing perspective. So this is not a talk about finances or how to make money out of Bitcoin, but this is a talk about how to demystify, better understanding maybe the underlying Bitcoin protocol. So you probably have heard about Bitcoin, maybe you have heard about blockchain, you may have heard about Ethereum, notions like proof of work, smart contracts, and so forth. And the goal here is to relate those notions to notions from distributed computing that would, I believe, help understand the above-mentioned notions such that the notion of a leader, consensus, snapshot, and broadcast. And the claim here is that by rephrasing or better understanding the above concepts like proof of work, Bitcoin, blockchain, in terms of consensus, leader, snapshots, not only one better understands the Bitcoin protocols and the hundreds alternatives, but also come up with better protocols, better alternatives to the Bitcoin protocols, which is what I will try to do in this talk. So the plan before diving into giving the distributed computing perspective, what I call the computer scientist perspective of Bitcoin, I would go back to some background on the Bitcoin system, virtual currency, as well as underlying protocol. And coming back to that will help me better maybe explain some concepts of distributed computing. So I will go through 5 perspectives on Bitcoin and the Bitcoin protocol. Of course, what interests me most is the last one, the computer science perspective, but I believe that the other perspectives are important to better understand this interesting concept of Bitcoin and Bitcoin protocol. So the first perspective is that of a journalist. This is basically a chat that one would have with a friend or member of the family about Bitcoin. And this would help me introduce at a very high level the notion of Bitcoin. So the historical perspective, 2008, the financial crisis. A lot of people in the world are accusing banks of stealing them or having stolen them or having stolen their retirement savings or whatever. So there was a crisis, and perspectives or a motivation on new forms of banks emerged. A paper comes on the web by an author called Satoshi Nakamoto. And this paper basically describes an alternative to classical banking. This Nakamoto, author of a paper, a white paper on the internet, claims to have invented an alternative bank. And this alternative bank is basically a peer-to-peer system where people would be able to pay each other, but without going through a bank, at least in the classical sense. They will be able to pay each other by going through a peer-to-peer protocol algorithm that basically is hosted not at some basic server somewhere in the world that belongs to some big company, but that is stored on all our computers. So the bank is all our computers. Initially, the Bitcoin virtual currency that was described in Nakamoto's paper was supposedly was planned to trade hardware, and initially it was done for that. So people will, I don't know, buy a mouse or buy some piece of hardware and pay with this virtual currency called the Bitcoin. But then rapidly people realized that actually the same scheme could not only hold for buying pieces of hardware, but also for buying pizzas, or maybe even buying a car, or even paying registration to some university. So the notion of virtual currency, introduced initially almost like a joke, became something very serious. And initially the Bitcoin, I think, the value was like something that one cent, and then it went all the way through $2,000, $20,000. Sorry, today I think in December 2020, I think it's around 16,000. So it's pretty high. So from one cent to 16,000 is pretty high. And as I will explain later, Nakamoto, whomever that is, actually saved for himself or for themselves or for herself 1 million Bitcoins. The total number of Bitcoins issued was 21 million, but one of them was actually owned in a way that I will explain later by the author of the paper and the implementer of the software. It is important to realize that there was a lot of speculations about who that person or that group of person is, and people have started all kinds of even legends sometimes about that person. It reminds me sometimes of this this personage in Usual Suspect, Kaiser Soze, or something like that never really existed, but was really there for the story. What is also important to notice is that this virtual currency, the Bitcoin, has actually the way it was implemented, used, has given rise to alternative currencies. One of them is Ethereum, which was also, I think, following the same path, although the goal was not only to pay each other, but also to actually execute all kinds of code in a way that is very similar, that resembles the way Bitcoin was implemented. This Ethereum concept was also a virtual currency, which these days I think costs around, the value is around $500. This was created in 2014, but the value now is $500. So the idea has really not only was interesting from the technological perspective, which I will talk about in this conference, but also from the financial perspective, because many people started imitating this idea. I just mentioned here one of these currencies, which is Ethereum. So in order to understand the idea of a virtual currency in general, and the idea of the Bitcoin protocol from a journalist perspective, from a high-level perspective, let me take you for a trip to Marrakesh. And this is a city you should visit one of these days for its amazing culture and atmosphere. So in Marrakesh, there is a famous place called Jam El Fna, which is central to the city, where tons of people gather. So they gather to play music, to tell stories, and also to sell all kinds of things. So you can go there and sell or buy whatever you want. Of course, you don't buy whatever you want, but you buy certain things that you find in that place. Among the things you find there are actually very beautiful carpets. And if you enter in the streets close to this place, you will find a lot of shops. Of course, they sell leather, they sell jalabas or things like that, but some of them actually sell very, very beautiful carpets. And one of these shops has a very smart owner who actually bought all the carpets from a certain area around Marrakesh. So you have to, for those of you who don't know carpets, the color of a carpet is intimately related to the place where the carpet was actually designed and manufactured. And this is very close. This is very special for each area. So you go to one area, you will find a specific color because the color comes from the actual nature of the land or water going there. So every area has a special color. So this owner of a shop in that place comes from some mountain close to Marrakesh, and he bought all the carpets coming from a bunch of villages, and therefore has some kind of monopoly on the color of the carpets. And the colors are really amazing, some kind of red. So this person has these carpets, which are unique. The business was going pretty well, and then this owner of the shop realized that maybe he could pay his employees with carpets. Instead of paying them with money, he could pay them with carpets. He wouldn't give them the carpet. He would simply write in a book that employee X now owns this carpet with that size. And then after 6 months, the employee owns another carpet. But you will tell me, why would the employee buy a carpet? I mean, the employees from that shop don't have huge houses, and they don't have space to put all kinds of carpets. In fact, they don't take the carpets from the shop. The carpets stay in that shop. But the fact that employee X, call him Omar or Ali, owns 10 carpets means something, because then that employee could pay other employees, or actually anyone in that famous Jam El Fna place can pay them with carpets. And the way the payment is actually achieved is by going to the owner of the shop and asking the owner, please, can you put in your book the fact that your employee Ali is paying somebody who's selling chicken 1/10 of a carpet against 10 chicken or something like that. And he would write that in the book. So that book actually registers all financial transactions that have to do with his carpets. So initially, he was paying his employees. His employees were maybe paying themselves, but then they started paying everybody in that place. And given that you can buy a lot of things in that place, people started actually doing all kinds of commercial activities by using this new currency, the carpets. And everything was written in the book of the owner of the shop. The owner of the shop plays the key role here because he owns the book. So it's a bank. The book is the bank, and that person is the owner of the bank. You could imagine that if Nakamoto, whomever that is, visited that place in Marrakesh, he would basically have warned the people in this place, be careful, you are putting all your economy within the hand of the owner of that shop. And that's very dangerous. Maybe you should actually keep using the currency you are using, but don't rely only on that owner of the shop. So what Nakamoto would have suggested is to actually build a peer-to-peer algorithm that would replace the owner of the bank. What could that algorithm be? In fact, it's actually pretty easy to imagine. Every person in the place who is interested in buying or selling stuff using that virtual currency will have a copy of the book. So a copy of the bank's book, that book which registers all transactions. So everybody will have a copy of the book. Of course, for this to work properly, a mechanism is needed to make sure that everything happens as if there was only one person owning the book. In other words, everything should happen as if all copies of the book look the same. If you have one copy of the book, things are easy. There is one bank, one owner of the shop. He registers all transactions. There is no cheating. Of course, he could cheat everybody else, but there is no cheating between people. If you build a peer-to-peer implementation of this and everybody has a copy of the book, you need to do something to make sure that I do not sell my carpet to different people at the same time. Because if I had a carpet and you have different copies of the book and I come to you and say, why don't you write in your book that I'm giving you this carpet and you give me your car? And I go to somebody else and I give him or her the carpet and I get something else. This is called the double payment or triple payment. Okay, this is something that can happen if we distribute the task of registering transactions. The way to circumvent this problem, to address this problem, is to mimic what the owner of the shop was doing. And the way to mimic that is to say, okay, for let's divide the time into periods, say 10 minutes, and every 10 minutes, somebody is going to become the leader, the main person who would initiate or write first in the book and then tell everybody else, here is what you should write in the copies of your book. Okay, so basically every period of time, let's say 10 minutes. Why am I using the 10 minutes? Because somehow I'm taking a period of time that is big enough such that if you register a transaction, you have time to tell everybody in the place. You tell somebody and somebody tells somebody in a gossip manner, oh, Rachid has given his carpet to Omar and has taken the car of Omar for that carpet. Okay, one transaction. And in 10 minutes, in a place crowded like that, everybody will know about it and Rachid will not be able to double spend. Okay, but we need somebody to somehow play the role of the leader and make sure that I am not able to do double spending. How can we do that? If you read Nakamoto's paper, you can actually get inspired from it and say, oh, it's very easy. Let's ask all people in the place who would like to play the role of the leader, of the owner of the shop for 10 minutes, to solve a big Sudoku, a big problem. And that Sudoku has to be very big because we don't want several people to solve it at the same time. We want one leader during a time period, and that leader will decide, okay, I am the one writing first in the book and then gossiping or informing the others about what I have written. everybody in that place knows Sudoku. So if you give them a huge Sudoku, they will try. And if the Sudoku is so big that you can only win by doing by filling it in a randomized manner, by just trying things without following a deterministic procedure, then you can actually guarantee that the probability of two people solving the Sudoku at the same time is very small. So by doing that, you can actually guarantee that you have one leader at a time during a time period, and that leader is going to register all transactions and inform everybody else about the transactions that occurred during that time period. Now, you could tell me, why would anyone basically would like to spend his neurons or cell to solve this big Sudoku? Why would we want to do that? Well, in fact, the answer is easy. You can have you can implement in your system a tax mechanism such that if you are elected leader and you play the role of the owner of the shop, then you gain some percentage of a carpet. And that percentage of a carpet is money somehow that you gain yourself. So when you write, Rachid has given his carpet to this person, then a tax comes to me. Me means the leader who solved the Sudoku. Of course, the Sudoku has this characteristic that when we solve it, it's easy to check that actually we have solved it. It's hard to solve, but when we solve it, you can just go through the lines and it's easy to see. So you have to imagine here a mechanism where the first person who writes in the book during the time period writes also in the book the solution of the Sudoku, and of course say, with this solution, I deserve to be the leader, and therefore I deserve to be the first one to write these transactions in the book, and therefore I deserve to get the taxes. Okay? So what I did here is give you an idea, gave you an idea about, hopefully, about what a virtual currency mean in the sense of Nakamoto, and what a peer-to-peer protocol would mean to implement such a virtual currency in a large-scale system where you have the ability to quickly exchange messages and gossip information. So the user, let's go back to reality. Let's go out of Marrakesh and go to reality, and now ask the question, but a concrete user, how does she actually play with Bitcoin or use Bitcoin? In fact, it's very simple. Just like you go to your favorite bank, I mean, you go to the internet, and then you have a client, a wallet from your bank, and you start using through some key, by entering some password and having some key, you start sending money and receiving money. A blockchain system or Bitcoin system goes exactly like that. You just have a wallet that you register through some identity, your password, and once you have that wallet, you can start sending money and downloading and receiving money. So the user of a Bitcoin system is basically a wallet. A wallet is, think about it as a way to enter to get access to the internet client that enables you to send money and receive money. And basically it means one private key, think of it as a password, and some public keys that people can address you to. From the client perspective, what you know actually, what is enough to know is that you basically go to your wallet, you sign a transaction saying, I'm giving my carpet to somebody who will give me a car. And you can actually, what you need to know is that something is going to happen. And after a while, 10 minutes, we have been using the 10 minutes, but it does not need to be 10 minutes. It's not always 10 minutes. It depends on how difficult is the Sudoku to be solved, but usually it's 10 minutes in Bitcoin. You know that during these 10 minutes, you are going to sign your transaction. Your transaction is going to get gossiped. Okay, it has not been validated yet. I'm simply telling the world, I want to give my carpet to somebody. And then there is the mining. The mining is the act of solving a Sudoku. So somebody around me will solve the Sudoku and will be the one writing my transaction on the book. Okay, so a bunch of transactions will be will be written by that leader who solved the Sudoku, and all those transactions written by that leader will be chained. We talk about a block of transaction, a blockchain in general, but a block of transaction. After time t, 10 minutes, thousands of users have seen what that leader has done, and all of them will write in their book the fact that I have given money to somebody. So from the user perspective, things are pretty easy. Now, what we call the participant in the Bitcoin protocol or the Bitcoin system is somebody who, I'm not talking here about the user who is going to give money or get money. I'm talking about the participant who is implementing the protocol. So that participant will have a copy of the book, and sometimes will try to be leader and write and be the first to write a bunch of transactions in the book. Okay, so the participant is somebody who is a miner. We say it's a miner because it will try to solve the Sudoku. The Sudoku is so big that the task resembles that of a miner who goes to a river and just try randomly to find where the gold could be. The key idea here that I pointed out earlier is that there is a difference between solving a difficult task like a Sudoku and checking it, verifying it. So if I tell you what are find for me the two integers of which product is 91, it will take you some time to find out that. If I tell you multiply 7 by 13, you will immediately get to 91. So this is the key idea here underlying the notion of participant or miner. It takes a lot of time and you need luck to find gold, to find the solution. But once you have found the solution, it's easy to convince the rest of the world that you have found the solution. And that the fact that you can convince them easily is crucial, because you write in the transactional book your solution and everybody will believe, will trust you, and therefore they will gossip and really write down the fact that Rachid has given a carpet to somebody. The way it looks in practice is something like this. Again, if I want to participate, then I have a copy of the book, but more specifically, I want to mine. I'm not going to a river, but I will download some piece of some internet client where I will try to find, it's not actually a solution to the Sudoku, but what we call a nonce, some number that satisfies some property. And for that, actually, these days, I would need a lot of computing power to have a chance to win, because I will have to try all kinds of integers. It's like solving a Sudoku, trying to find all kinds of numbers. And here, it's not an integer, it's actually a real number. I will have to try a lot of formulas in a short lapse of time to have a chance to win. But this will basically consist in just getting a number of a transaction block for which I need to solve the problem, and then try to solve the problem. There is something important here that I should quickly go back to. This Sudoku here is, it is important that it be triggered or generated online. What I mean by online is, in order to avoid that somebody goes home and try to solve Sudokus and come and cheat and be leader for a long period of time or whatever, the Sudoku actually is generated based on the transactions that are being produced by the users on the fly. Okay, so this is very crucial. And here, when I was talking about the participant who connects to the internet and say, oh, I want to try to solve Sudoku to find this magic number called the nonce, it cannot do that the day before, because the problem to be solved is intimately related to the actual transactions to be executed. And those the actual transactions are actually are being proposed by users on the fly during that very time. I cannot actually know in advance who is going to send money to whom. So to validate a transaction, a miner has to solve a puzzle. including that transaction. So that's the online. So there is a notion of fairness, if we want, because everybody is basically starting from zero, from scratch, to find. Of course, if you have more computing power, you have better chances, but at least you are not getting an advantage with respect to knowing what the transactions will be. And there is, of course, some kind of cooperation because we all try to implement the system. So today, the incentive you have to try to solve the problem is you get slightly more than 6 Bitcoins whenever you solve the problem for a block of transactions. This number has diminished. 3 years ago, you would have gained 50 Bitcoins. I told you earlier that initially there were 21 million Bitcoins generated. 18 of them have been already used, which means that whenever people have mined, they have gained some Bitcoin. So there are 3 left. I told you earlier that Nakamoto got for himself or from themselves 1 million. How? By generating a bunch of initial transactions and mining them. So if I was alone in 2008, just together with Nakamoto, maybe I could have mined as well and maybe got 500,000 or something like that. Now, Nakamoto was alone, so he was mining alone, so he was getting that million. So this was the user perspective and the participant perspective. The engineer perspective here, I'm going to go quickly, but it is important to know that there are some almost standard mechanisms that are assembled to make things work. The notion of a peer-to-peer network is classical in computing. It's basically a network without a central server, and people can just interact, exchange messages, and sign messages. So signing is also something crucial. The notion of signature is classical now in computing. It's basically a mechanism that enables you with very high probability to secure some information and make sure that nobody can pretend to be you. So this is basically the idea. It's just like having a password when you go to the gym, and you use that password with high probability to ensure that nobody's going to use your to access your cloud. And then another concept that is crucial is that of gossiping. So the notion of gossiping here means that when I send money to somebody, it's basically, it goes to writing a transaction and then sending the information randomly to some neighbors, and then the neighbors will do that randomly to another neighbors, and the power of exponential gossiping will guarantee that the information will go through all the system. There is this idea of gathering a block. I told you earlier that when somebody solves a Sudoku and write a transaction, he or she doesn't only write one transaction, but actually a block of transactions, okay? So this is the notion of gathering, and that's why we talk about blockchains. We chain a series of blocks. There is this idea of mining, we call it proof of work. The notion of proof of work means that somebody had to spend some computing power to solve the problem. So the way transactions, the way the financial system work is by joining, signing transaction, gossiping the transaction, gathering transaction inside the block, mining to make sure that only one person is going to place the block inside the book of transactions. Once this is done and a Sudoku solution has been found, this solution is chained also to the block, and now the block is gossiped in a validated sense. So when you reach this step, gossiping the block, this means that now the transaction has actually been validated because some leader, some participant has solved the Sudoku and was able to validate by putting the solution to the Sudoku and associating it to the block. And this is usually committed. Sometimes we talk about aborting if either there is an invalid bank account, or there is not enough money in the bank account, in the account, there is no bank in the account, or there is a probability that you have several leaders and there are some mechanism to make sure that eventually we go back to a situation where only one leader is winning. I'm not going to describe that mechanism called fork mechanism. Here, I don't think it's very important for what I'm going to say. I'm going to skip these ideas of hashing. I think you probably have seen that as well. What is important here to realize is that the book of transactions that I was talking about is more like a book of blocks of transactions. Every block starts with the reward, and this reward is related to the leader, to the person who was able to solve the problem. So this block somehow is associated with one leader, with the miner who was successful. And the block starts with the reward and then a bunch of signed transactions. So it's signed because there is somebody who has signed this transaction saying, I'm sending my money to somebody else. So you have a bunch of transactions. And here the validation of this block is builds upon the solution of the Sudoku. The solution of the Sudoku is this number, the nonce that it's called the nonce that has been found. And all the blocks are chained. So this is the previous block, and this is the current block, and there will be another block. And all these blocks are chained, are related by solutions of the Sudoku. And the solution of the Sudoku is somehow the identity of the leader. Okay, so this is basically saying, oh, I as a leader was able to find this solution, and this is easy to check this solution. You can just see the solution of the Sudoku and say, oh, this is a valid solution, and this is a validation of this block. Okay. As I pointed out earlier, after the Bitcoin system was released and used, people started thinking of alternative or for other applications of the same kind of scheme beyond payments. And in fact, a generalization of simple payment is that of a contract where not only you say, I'm giving my carpet to somebody, but you are also saying, I'm giving my carpet to that person, and within the same transaction, and that person is giving me back a car, which was not in the original contract, in the original transaction. In the original transaction, there was only the payment, what I was talking about. The notion of contract includes things like, I'm giving this carpet to this person, and this person is giving me something back, and somebody else is going to also benefit, and this and that. You can even add conditions if the weather is nice, and this can only be executed next week if it rains or whatever. The notion of a contract is somehow a generalization of a notion of payment transaction. And in fact, you can use a protocol that is the same as what I presented with the notion of leader. And instead of having only payments, you can have general purpose contract. We call them smart contracts. And the Ethereum system that I mentioned execute these contracts. So now I presented the journalist perspective, this shop and carpets and whatever, the user perspective, somebody who would have a wallet through which he or she can send money using the Bitcoin system, the participant who can mine and also benefit from the system if lucky, and also mentioned some mechanisms that are underlying this system. I call that the engineer perspective. So now I want to spend the last part of this talk talking about the computer scientist perspective, the distributed computing perspective. If you look at, if you know about computing and distributed computing, you can easily see that what's going on in the Bitcoin protocol is a state machine replication scheme. What does that mean? It means that we basically replicate a state, the transaction book, among all nodes of the system. It's like a state, and we make sure that everybody executes commands on this machine, transaction payments, in the same order. Okay, how do we guarantee that everybody execute in the same order? Because we have a notion of a leader. And the leader, we have that leader for a given point in time or a given period of time. But during that period of time, there is only one leader, and that leader decides the order according to which we are going to execute commands on the machines or transactions. In fact, that leader guarantees that everybody agrees on the order according to which we are going to execute transactions, or in the case of smart contracts, any program. So what's going on and behind the scenes is what is called in distributed computing state-machine replication. And this idea dates back to Leslie Lamport in a seminal 78 paper. Other papers comes after. And the problem solved by state-machine replication is that of consensus. Okay, so the consensus problem consists for a set of nodes to agree on something. They agree on the order according to which they execute the commands. And the problem of consensus is known to be universal. What does that mean? If you can solve the consensus problem, if you can agree, if you can have a set of processes agree on something, then you can take any centralized problem and distribute it and make it highly available. This is exactly what we did here. We started from a single bank, okay, the owner of the carpet shop, and distributed it. We distribute its role by solving the consensus problem. How did we solve the consensus problem? By electing a leader. Okay, so this is crucial. So what we are solving is the consensus problem. And once we solve the consensus problem using that leader, we can do payment, but we can do everything. We can do smart contracts or what have you. We know that consensus is hard. In particular, in certain settings, for example, if we don't make assumptions about time, so here I have been saying 10 minutes and this and that, but if we consider a general purpose distributed system where we don't make any assumption on the time it takes for a message from node A to reach node B, then we know also that the consensus problem is impossible. This is a famous result that has been proven in the area of distributed computing. So the fact that the problem is impossible actually means that it is hard. Okay, the consensus problem requires some synchrony, which makes the problem hard. So you have to make some assumptions, and even when those assumptions you can make them, this translates into complex algorithms. And not surprisingly, indeed, the algorithms that implement Bitcoin, they might look simple, but they're actually complicated. First, they require some assumptions about time. I have been assuming that people can relatively quickly gossip and exchange information. The algorithms are also expensive. Mining is very expensive. Electing a leader is expensive. So if you take the original Bitcoin implementations, the energy spent mining is huge. I think some journalists and some reporters have been saying that last year the energy spent on Bitcoin mining is the same as that of a modern industrial country like Denmark or something. So it's huge. So it's not a very green solution. So people have been looking at alternative implementations without mining. So they looked, and in fact, given the popularity and of this idea of distributed peer-to-peer banking system, tons of implementation, thousands of implementations of Bitcoin-like protocols have been proposed. Some using proof of work, just like what I presented, the fact of mining. Others used what is called sometimes proof of stake. Proof of stake means the leader is the richer person. Others used subcommittees where the leader has to be selected among a smaller bunch of committees at the expense of some fault tolerance, fragility. In any case, there have been tons of implementations. And what is actually not surprising in retrospect, but you have to realize, is that a lot of the effort spent today on those algorithms and implementations is to try to make sure they are correct. We believe that the original Bitcoin protocol is correct, but we know that it's very expensive, and it might not have been designed for so many users. So it doesn't really scale. When we scale it, we have energy problems. There are alternative solutions that are cheaper, but usually, and most of the time, they're not correct. So today, what is, I would say funny, but maybe not funny, is that a lot of companies and open source associations who come up with Bitcoin protocol alternatives have a hard time proving that the algorithm is correct. So these algorithms are usually a mess. And why are they a mess? Because they solve a very difficult problem. They solve the consensus problem, which I told you, sometimes it is just impossible. So if you believe you solve it, then you are not solving it. If you make some assumptions that circumvent the impossibility, then the algorithms actually turn out to be complicated, unless you make very, very strong assumptions, in which case the solution is not realistic. So I believe that the perspective of the scientist, of the computing scientist, is to try to understand whether the Bitcoin problem has to be that difficult. And the question I'm going to ask in the last part of this talk is, can we implement a payment system asynchronously? The consensus problem cannot be implemented asynchronously. Okay? It is a synchronous problem. It requires a leader. It requires synchrony, and therefore it is difficult. But that is because we wanted to implement the payment system using consensus, that we ended up having a hard time implementing it. But can we implement a payment system without going through consensus in an asynchronous manner? In classical computing, the world is divided into problems that are easy to solve and problems that are hard to solve but easy to check. Okay, so multiply 7 by 13 is a P problem, is easy. Finding the two numbers of which product is 91 is a hard problem. In distributed computing, I like to think that the analogous distinction or classification of the world is between synchronous and asynchronous. Synchronous problems are hard, NP. You need consensus, you need timing assumption, you need leadership. Asynchronous problems are much easier. So is payment an asynchronous problem? Where does payment, what I call the payment, is more specifically the problem posed by Nakamoto, which is called actually the double payment. But this is the problem solved by the Bitcoin protocol. Is it a synchronous or asynchronous problem? Lannister said, to understand a distributed computing problem, bring it to shared memory. Okay, so that is something very important. I hope you know who Lannister is. When we usually talk about the Bitcoin problem, we assume a large number of nodes, a large number of processes communicating, and these nodes are geographically distant. I send money to somebody in Australia who send money to somebody in the US or whatever. So this is a large-scale system. Reasoning about problem in large-scale system is not always easy. In fact, it's usually difficult, especially because we typically assume that some of these nodes, some of these processes can be very malicious, can be very hard in the sense that they can have a strong power. We call the set, the coalition of people who want to do double payment and cheat, we call that an adversary. And we say that the adversary can be very malicious. It turns out that when we do distributed computing, sometimes we look into the infinitely small, meaning we look inside one computer and study processes accessing the same shared memory. Here, processes are not really malicious. They can be slow. So the adversary, okay, the entity that models what can go wrong, is somehow weaker. It has weaker power than the stronger of the large-scale system. Furthermore, whereas in the infinitely big world, processes exchange messages, nodes exchange messages, in the infinitely small world, they read and write in the same shared memory. So these are two perspectives of distributed computing. In fact, in the second case, we talk about concurrent computing. So message passing is the model where the Bitcoin problem has been initially presented. Processes, nodes exchange messages, and the adversary can be very, very bad. It can corrupt some processes who send messages they were not supposed to send. Shared memory is the model that you typically adopt when you have a single machine with several processors, And here, P1 and P2 are two processes of the same machine, and they read and write in the same registers. So they have a memory composed of registers. This memory is shared, and they write and read it. And here, what happens to these processes, the worst that can happen to them is they can sleep for a long while. They are not going to, well, in general, we assume that they're not going to try to cheat the system. So the adversary is weak. One of the most fundamental results in distributed computing is actually that a message passing model is equivalent to a shared memory model. What does that mean? It means, in fact, that we can emulate a shared memory in a message passing system, what I call the infinitely big, assuming I have a quorum of correct nodes. So if I have, let's say, 100 nodes in my large-scale system, and let's say I have enough of them that are correct to constitute a quorum. Quorums are sets of which that intersect, and more specifically, in the case of an infinitely big system with malicious players, I can guarantee that such a system can mimic a shared memory system if I have quorums of which intersection contains correct processes. I'm not going into the details here, but if I have an assumption about enough correct processes, then I can build a shared memory. Okay, so you have to trust me on this. This is one of the fundamental results in message passing, how to emulate a shared memory. And the idea, for example, if you have a weak adversary, is to assume that you have a majority of correct processes. And to give you an intuition, if you want to emulate the act of processes writing in shared memory, you send a write message to all, and you wait for a majority of them to tell you we have this information. And therefore, when somebody wants to read and reads from a majority, given that the two majorities intersect, the reader will find the right value, as if it was reading in the shared memory, something written on a shared memory. Okay? If you have a malicious adversary, you need more correct processes than a single majority. Usually you need 2/3 to make sure that the intersection contains correct processes. This is not a rocket science, but it's fundamental distributed computing result that message passing and shared memory are equivalent. Of course, you can tell me, yes, but if we throw your equivalence, maybe there are a lot of messages going, and if you start with a problem solved in this, for example, in the shared memory world, and you port it to the message passing world, then this will be very expensive. Of course, but here, let's not worry about complexity of sending messages or whatever for now. We are just trying to address the question, is the payment problem asynchronous or not? So the payment system is what Nakamoto defined in his paper. And we want to ask whether it's an easy problem or a difficult problem. I said easy means asynchronous. We can solve it. We don't need consensus. We can solve it in an asynchronous manner. And there is actually a precise way of asking the question of whether a problem like that is asynchronous or not in shared memory. What do we do? How do we proceed? We typically define the payment system as an object, like in classical object-oriented computing. And now we say that this object can be accessed as if it was in a shared memory by several processes. And we want to guarantee that the access of those processes is atomic, meaning every process feels or access the object as if it was alone, but in a wait-free manner. Wait-free manner means, indeed, we access the shared object as if we were alone, like if we were locking it, but we don't lock it. If you don't know what locks are or forgot, don't worry. What I'm saying here is the fact that we have a clean way of asking the question whether a payment system is asynchronous or not in shared memory. We define two notions, atomicity and wait freedom. They also date back to Lamport, and they have been refined by Maurice Herlihy. So can we implement a payment system asynchronously? This question translates into, can we implement a payment object in an atomic and weight-free manner in shared memory? So in order to address this question, let me address a slightly different question that is easier maybe to understand, just in order to understand the very nature of the question. Think of a counter. A counter is an object that has two operations, increment and read. The payment system is slightly more sophisticated, but you can view it as a counter. I will come back to that. A counter object maintains an integer x initialized to 0, and you can increment it and read it. When you read, you return the value. When you increment, you add 1. And you can ask the question, can we implement this object asynchronously? Is this object difficult, NP in the distributed computing sense, or P? It turns out that it's easy to come up with an algorithm to implement the counter in a shared memory system. You have n processes. They all share an array of registers. When a process PI increments, it goes to a register and it increments the previous value. When you want to read the value of the counter, you sum all the counters. So what am I doing here? Okay, let's go back. I want to implement this object counter in shared memory, and I want the object to be accessible by n processes in a weight-free atomic manner. If I implement this counter in one single register, I would run into troubles because maybe a process comes, reads the value of the counter, finds the value of the counter 0, and wants to increment it, but in the meantime, other processes come and concurrently increment the counter several times, put the value of the counter to 6, and now I put it back to 1. So this is not atomic. If I want to prevent this case, I can use locks, but this is not weight-free anymore. This idea here of saying, let's have different pieces of the memory, and each process has its own piece and increments its own piece. When we read, we sum. Now we have implemented a counter in an atomic and weight-free manner. Good, which means that the counter is a simple problem. It's a simple object, it's an asynchronous object. What if I have counter star? Counter star has, in addition, operation decrement. Okay, so the previous counter has read increment, now I have decrement. If x is bigger than 0, then I can remove 1 from the counter, else I cannot. I can ask now the question, is counter star asynchronous or an asynchronous problem? Is it a hard problem or is it as simple as the counter? It turns out that the answer to this question is no. We cannot implement a counter star asynchronously. It is a difficult problem. How do we prove, how do we show that counter star is difficult? Actually, we show that if I could solve counter star, I could implement consensus among two processes. And I'm going to show you how to implement consensus among two processes using counter star. Every process who wants to solve consensus propose a value. So let's assume two processes, they want two persons, they want to go to the movies. One of them says, I want to see James Bond, and the other guy says, I want to see Asterix. So both of them propose a value. The algorithm is the following. Each of them writes its own value in a register. And then they go and they access this counter star. The counter star is initialized to 1. They decrement the value of the counter. Given that the initial value is 1, one of them will get OK, will be able to decrement. The other one will not be able to decrement. The one who will be able to decrement has succeeded, has won. It will decide to see the movie it initially proposed. The other guy who lost, who won't be able to decrement, will find the movie to watch in the other register. What I have done here is I have shown that if I have a counter star, I can solve consensus. But given that I know that there is no algorithm that solves consensus among two processes using registers, I know that no asynchronous algorithm implements counter star among two processes. Counter star is asynchronous problem. So counter and counter star look very similar. But counter star has this operation decrement, which makes it, in fact, significantly harder. It makes it a synchronous problem. It cannot be solved asynchronously. By the way, something important here. I told you that this counter star enables you to solve consensus among two processes. In fact, it can only solve consensus among two processes. You have object that can solve consensus among three, other object that can solve consensus among four. Maurice Herlihy has defined the notion of a consensus hierarchy, where you can classify objects not only whether they are easy or hard, but those that are hard, you can also classify them according to their hardness. And the hardness is their consensus number. Just like the atomic number with Mendeleev's table, here the consensus number is how many processes can solve consensus using that object. I will come back to that later. So now, an object that resembles the counter is the payment. So payment is an object that has an integer as a state, but here you don't really increment. You transfer amount x from A to B. If A is bigger than x, a little bit like counter star. However, unlike counter star, only the owner of A, so we have owners, processes are somehow owners, only the owner of A can invoke pay A. So only I can send my carpet to somebody else. And now the question is, can this object, payment object, which I call, can it be implemented asynchronously? Or in other words, what is the consensus number of this object? Okay, is it 1, which means that the problem is very easy, or is it 2 or more than 2, which means that the problem is hard? Counter has consensus number 1. I cannot solve it, I cannot use it to solve consensus among two processes. The P object has consensus number, I don't know, I'm asking the question here. If it was 1, the problem is easy. If it's more than 1, the problem is hard. I'm not going to go into details, but I'm simply going to claim and to show you that if we implement another object, which is called atomic snapshot, we can implement the payment object. And that object called atomic snapshot resembles the counter in the sense that it's easy to implement. So a snapshot has an operation update and scan. Okay, so snapshot, you can view it as the set of all Facebook walls of people involved in some social network like Facebook. So the snapshot is like the sum of all the walls of Facebook people. Everybody can update its wall, and at any point in time, I can scan the entire walls. So it's like everybody can act like Mark Zuckerberg and scan all the walls. I'm not going to show you how you can implement this object in a shared memory setting without solving consensus, means asynchronously, but you have to believe me that this object can be implemented. I will share the slides, and the slides give basically an algorithm that is actually very smart to implement this object in a weight-free and atomic manner. Roughly speaking, we have an array of registers. Everybody has its own register where it writes its own wall. And when I want to scan, I basically read all the walls and check if 2 are the same. I know that if 2 sets of walls are the same, I know that it's atomic. Okay, this is the main idea of an algorithm to implement the snapshot. It turns out that this algorithm might never terminate if it's just what I presented. In fact, I need to add to this algorithm the idea that everybody who wants to update has to try to scan. And that will guarantee to me that if I'm not able to scan because I cannot find 2 sets of wall that are the same because somebody is updating, I force the process to update to scan and to give me back the scan. The algorithm is presented in these slides. To scan, a process keeps comparing sets of collects until it finds two that are the same. If it does not, this means that somebody is updating, but I'm going to force the process to update, to scan and return the value. It turns out that if I can solve the atomic, the snapshot object, which I overview how I could solve it, I can actually implement the payment object. How? Every process stores the sequence of its outgoing payment in its wall. Okay, it's as if in Facebook I say, I have given money to this person, that person, that person. Whenever I want to pay, a process scans, computes its current balance, because if I know exactly how much money I have given to whom and who has given me money, I know exactly whether I have the right to give money to somebody or not. The book of transaction is the atomic snapshot. Remember the book of transaction. It turns out that what I'm saying here is the book of transaction resembles the atomic snapshot, which is an easy object. So the payment object can be implemented asynchronously. Its consensus number is 1. Okay. In fact, I can even generalize this result by saying if I have K people and they all are involved in some transaction, this one pays money to this one and that one pays money to that one, etc. The notion of smart contract that I was talking about earlier. If these people, the number of them is K, then the consensus number of this object is K. But if there is only one process, one person who can send money to somebody else, as in the original Bitcoin protocol, the consensus number is 1. So why is that important? That is important because now we know that the payment system is actually does not need to be that complicated. The payment object is an easy problem, so we can implement it in a rather easy way. And in fact, in our lab at EPFL, we were able to implement several variants of the payment object. Of course, what I call S here is the shared memory variant, which I overviewed. Once you implement the atomic snapshot, you can implement the payment object, but you can even go back to the message passing system and implement actually variants of the payment system that are actually much easier to understand than the classical consensus based implementation. You can show that you save at least one order of magnitude lines of code in terms of numbers of lines of code. And in terms of latency, you can actually be much faster than consensus-based solutions with the same reliability. So for those interested in understanding the notion of why the payment object is easy, there is a paper that we have written in PodC 2019 with colleagues, current students and former students from my group, called The Consensus Number of a Cryptocurrency. It's available on the web at ACM PodC 2019. This paper describes what I overviewed, which is you can implement an atomic snapshot easily. This is a known result. Once you have that, you can implement a payment object. Then there was one application of that object in the message passing world, of that result in the message passing world, with again, current and former PhD students, showing how you can leverage that result in shared memory in message passing and build a scalable payment system. In fact, we have shown that the payment system is some sort of reliable broadcast, which is known to be easier than consensus. So this paper shows how you can build a payment system in a scalable manner, and the paper got a best paper award at DISC. This was a rather theoretical work. We went a step further and we implemented this with more students from the lab, and implemented a payment system, and have shown practically that it's almost the same as a broadcasting messages. So this appeared at IEEE DSN, the last one. So all these 3 papers are available on the web, and you can look at the theory part or the practical part. There is still a lot of work in the lab on this problem, and in fact, we have released an open source library implementing variants of various payment systems, and you can actually download the code from the lab and play with it. more references. I really believe that understanding the foundations of concurrent and distributed computing would help understand problems like Bitcoin, smart contracts, Ethereum, and things like that. I really believe that these concepts of concurrent and distributed computing help you understand those concepts.
Hi, Rachid. How are you? So great to have you here with us. Thanks.
Thank you. Thank you. Thank you very much.
Yes. So thank you very much for your charming talk, your great results about Bitcoin, the Bitcoin protocol. And I think that you succeed to explain with a very ludic history regarding your native country, Morocco. And the protocol is really complex, so we can follow all the idea and until arriving at this such great result about Bitcoin. So indeed, we do not have to make a consensus to solve the Bitcoin problem. So that's great. So that's something that I think that can change now what we can do with payment systems. So you do not have the need to have such wasteful protocols. So like the Bitcoin with mining, this mining stuff. That's it. So are you listening to me?
Yes, I can hear you.
You can hear.
Yes. So which question you want me to address? The ones on the chat?
No. Just to begin, I have two questions here in the chat. I'd like to encourage people to ask questions and comments. But before beginning,
yes,
from the distributed community perspective, in your opinion, what are the main contributions of this work of Sakamoto, of the Bitcoin protocol? Just to start the conversation.
No. This is a very good question, and in fact, if we think about it, and I believe it is very unfortunate, maybe the paper of Nakamoto, if it was submitted to a distributed computing conference, maybe it would not have been accepted, because if you think about it, it doesn't present anything particularly new. It's an assemblage of various ingredients together. But this assemblage is amazing, is fantastic. And unfortunately, we tend not to consider as good if you don't have one particular contribution. So the contribution is putting things together and showing that it works, showing that you can scale them to some extent, scale them for some number of processes, etc. So that was, to me, the main contribution of Nakamoto's paper, showing that distributed computing as is can be actually used in a large scale.
Oh, that's good. So let's address these questions from the audience. I have a question by Célio Albuquerque, our colleague. Célio says, thank you very much. Thank you for your nice and ludic presentation. 10 minutes is still necessary in real-world peer-to-peer consensus? Please comment on the scalability and on Bitcoin's throughput in terms of transactions per second.
To be honest with you, I don't know whether it's still 10 minutes today on Bitcoins to mine, etc. It was like that few years back. I suspect that it's still the same. And again, the idea is what I try to present by this analogy is that you need time for somebody to mine and find that famous number, the nonce, or solve the Sudoku, and then disseminate large enough the information such that it prevents double payment. So I think it's still the 10 minutes. As for the bandwidth, I think the bandwidth was pretty good recently, but the problem was more the energy problem, because as you probably realize, mining has a cost, and I have read somewhere that the energy spent to mine, solve those Sudokus is equivalent of that of an industrial country. So that is just crazy. The energy used by the computers who are heating up to solve the famous Sudoku. So that was a big problem. Of course, if you understand that you don't need to solve consensus, this means you don't need a leader. This means you don't need to mine and so forth. So you don't need to spend that energy.
Yeah, that was what I was commenting before the questions. So that's great. Knowing that, that's great for us, but I don't know if it's great for the industry. I have another question from Rafael Pir. Hello, Rachid, thanks for the talk. Being decentralized, how come the Bitcoin rewards for the puzzle winner has come down from 50 Bitcoins to 6.15? That is, who decided that, and how was it enforced to put the peer-to-peer network? Is there some sort of agreement on the reward?
Yeah, very good question. In fact, there is no agreement on the reward as far as I know. There is more some parameters in the algorithm itself that was published by Nakamoto that relates the reward to the difficulty of solving the mining. So basically the algorithm looks back in real time on how long it took to find the last nonce, or to solve the last Sudoku. And if it was too fast, then it is made hard, and the reward is made smaller, etc. So it's in the original algorithm. Given that everybody executes the same algorithm and there is some assumption about time, you almost obtain this agreement you are talking about.
Yeah, good. So I have another one from Alan Freitas. Great lecture. What is your view about other approaches for distributed ledger technologies like IOTA in comparison with Bitcoin approach?
Yeah, I'm ashamed to say that I don't know IOTA. I have no clue. If you can tell me what it is, I can react. But to my knowledge, most of the work, unfortunately, have been following the original papers and trying to optimize consensus rather than question the need for consensus. So maybe IOTA is not in that direction, and I have to apologize and say I don't know it.
Okay, I think that the question is to compare perhaps blockchain approach to solve the payment problem, and solutions that use DAG or directed acyclic graphs in this case, because IOTA has this Tango protocol.
Okay, now I understand. Yes.
The DAG,
Yeah. That I understand. So again, I don't know what it is exactly, but my thing is that if you avoid consensus, you typically end up with much simpler solutions. And I think simplicity here is even more important than latency or throughput. Why? Because the complication of the code of those companies running the Bitcoin today is so huge that they don't hire system people to speed up performance. They hire verification people to prove that the algorithm is correct. So making it simpler, and if IOTA and DAGs make it simpler, then I think it's already a big achievement. Even if sometimes the latency you don't gain a lot, it's not that important in my opinion.
Yeah, but do you think, Rachid, that most of these works that we are aware of, they are trying to solve consensus, but indeed they can solve the simple payment problem? Do you think that is the case? So
yes, they solve the simple payment problem, because once you solve consensus, you have like a universal machine where you can solve everything, but you have too much. And
Yeah.
the algorithm needs to be Paxos-like or whatever with eventual synchrony and this on that, and that's where the problem comes. We don't even have a single proof that these algorithms work if we consider safety and liveness, so it's very, very hard.
Yeah. Right. We have another question from Mateus Ferraroni Sanchez. Thank you for the presentation. It was really good. Can you talk about if there is a problem about the centralization of the money in Bitcoin?
Oh, good question. Yeah, you're right that the original motivation of Nakamoto was to say we don't want to centralize money, we need to distribute. But when we see today how Bitcoin is used, I mean, it's not used, how it is mined, only few places in the world have enough computing capacities to mine faster than the others. And in somehow we replaced banks with big clouds or computer centers. There are some villages I've heard in China, they have put together the computers so they can be very fast, and there are some centers maybe in Scandinavia. So we replaced the centralized system with another centralized system doing something different. So in a sense, maybe we failed. Maybe Nakamoto would be unhappy if his goal was not to make money but to have a decentralized system. I don't know what the goal was.
Yeah, thanks. Another question from Gabriel Quaresma. Thanks for the presentation. It was very good. Do you think digital currencies like Facebook's Libra can encourage people to switch to digital currencies, since digital currencies like Bitcoin are more reliable than Brazilian real or even dollar?
Yeah, a good question. Again, I'm not a financial expert, but if you think a little bit about it, the fact that the American government and other governments are so against the Libra is precisely because I think they believe, and I believe they're right, that immediately people will start paying each other on Facebook with Libra. It would be so easy when you say, like, I say, okay, I can send Fabiola $5, and then she would bring me something from Brazil or whatever. So it's, I think there is a big risk there. Whether it's a good thing or not, I don't know. Whether the Bank of Brazil is more trustworthy than Facebook headquarters, I'm not sure.
Okay, thanks. I have another question from Amanda Oliveira. Hello. Even though I can understand why an asynchronous approach has several advantages, I don't know if I understood why there is such a need for mining in the first place. Why couldn't the current leader be responsible for selecting the next leader? It is due to possible malicious users.
Yes, absolutely. Because if what the Sudoku or the mining introduces is the fact that anybody, in principle, anybody could become a leader, and therefore, if I am malicious, I don't have any guarantee that I become the leader, and I cannot even go and bribe Fabiola and this and that person and tell them, okay, we are going to constitute a coalition of leaders and we're going to steal the money. We don't know whether we will be elected by the mining process. If I'm leader and I elect some leader, then I can screw up the entire system.
Yeah. Let me ask you another question. You proved that you can implement a payment system synchronous, but it's not clear for me if you can implement smart contracts asynchronous. What are the difference between them?
Yeah, very good question. Typically in smart contract, you have several people who own the same money somehow, whereas here there is one person. And one of the generalization of our result is that if you have a contract involving K people that have the same account, then you need to solve consensus among K. But you don't need to solve consensus among the entire set of system, the entire set of processes. So it's more reasonable.
Yeah. I don't know if we are arriving at the end. I don't know if Marcelo, which is here, Marcelo Amorim, the organizer of our keynote,
I see that he has a question
here with us.
I see that he has a question that simplicity is the most important aspect, much more than latency. So what could we, from the networking community, do to help the payment problem you discussed today? I think it's a very good question from Marcelo. very, very good. I think the networking community, they could probably look a little bit into what distributed computing people are designing, and maybe the networking people can build the abstractions that we need. For example, if we realize that, I don't know, I'm simply saying Byzantine reliable broadcast is very important, then maybe the networking people can build a very powerful, scalable Byzantine reliable broadcast, and we can use it for payment systems. That could be something, just like they built TCP/IP, they could build more broadcast-oriented protocols that are Byzantine resilient, and we could use them.
Yeah. All right. Thank you very much, Rachid. We are at the end. So, very good presentation. Thank you so much for being here with us. I guess we can start.